Hi there. I'm bringing you my video of Unit 5 from my backyard. It's a beautiful day. You should get outside. Here's my backyard. I don't know. There's like a big old woods. I live on a 2.5 acres. Beautiful. Okay, so this Unit 5 that I want to talk about is three things. The reaction coordinate diagram, which is what you see here. Number 2 is about finding the rate law, whether you have the rate determining step or not. And then number 3 is about the graphical analysis about the rate laws. So let's start with this one. I want to look on the right-hand side of the reaction coordinate diagram and hit a couple of things. First thing is about activation energy. So this one in here, the first step has this for an activation energy. The second step has this much for an activation energy. You can see the first bump is bigger, therefore that's the rate determining step. That determines how fast the reaction goes. That would be called the slow step. It's different than the one on the right. The one on the right you can see has more bumps. Here's the first activation energy, the second, and the third. I can see the middle bump is the highest, so therefore it has the greatest activation energy. Therefore it's the rate determining step, or the slow step. Something to note about these sort of things is as you increase the temperature, you are going to increase the rate of the reaction. And that's because it's more likely that you'll have enough molecules that can get over the bump, that they have enough energy in their kinetic energy, their speed, in order to get over that activation energy barrier. So that applies. Something to note about each of these is we've got intermediates. This little bumps down here that I'm putting in green, these are the intermediates of these reaction coordinate diagrams. Those things that live temporarily. These top parts up here are actually called the transition states up on top. And they're different. Okay. Neither of these reaction coordinate diagrams are showing catalysts, just to throw that in there. So let's take a look at our reaction mechanisms over here on the left-hand side. I'm going to first look for transition states. I can see in this one, Cl goes in, plus O3, those are two reactants, and they make these two products on this side. If I look at the next part, I can see, oh man, ClO is made, and then ClO is consumed. If you make it and then you consume it, that's a transition state. That's these green bumps right here. That's my only transition state because O2 isn't consumed here. What I can see, though, is that I have a catalyst, and I know that because when I put in chlorine, I get chlorine out. That's indicative that it's a catalyst. A catalyst means you put it in and you get it out at the very end, not in between. You put it in the beginning, you get it out at the end. That's a catalyst. The transition state is made. That does not look good. So let's look at the bottom one down here. If I'm looking for a transition state, I want to make it. Here I made it, and I want to consume it. Here's my transition state. I don't have any others. This N2O here isn't consumed, so it's a product. I'm not going to see it on this other side because it's not part of that second step. So the N2 is a product, and the H2O is a product. I do not have any catalyst here, and I know that because it's not like I put in NO and H2 and get it on the other side. My reactants in this case are NO and H2. H2 is a reactant here too. It's nothing really funny. It's just a reactant also in the second step. My reactants of this top one are these yellow ones. And then the products is H2O on the bottom, and N2 is a product. This part here, I've got O2 as a product both times. I think that's all I wanted to cover on that part. Yes, okay. Now I want to talk about the rate laws. So I got a rate law whether I've got the first step as a fast step or not a fast step. So taking a look at this. These ones over here, what if I wanted to find the rate law for this? The basic, I've got two problems. My rate law is going to be dependent on my slow step. So I'm going to write it as I find my slow step. If you're asked to find the rate law for an elementary step is each of these parts. Or I could say in a problem, I give you the elementary step, find the rate law. You can always find the rate law for an elementary step. You can't find it for an overall reaction because you don't know the mechanism. Now here, on my left-hand side, I've got three, so I've got a mechanism. It's made of elementary steps. That's the word. Made of elementary steps. I see my slow step is first. A part of the rate laws, all you got to do is write rate equals K times, and then I want to use my reactant of my slow step. Here my only reactant is H2O2. So it's the concentration of H2O2, or hydrogen peroxide. There we go. And then I check, and I'm like, yep, H2O2 is a reactant. I can use this as a rate law. I'm done. The K here, to bring it back to temperature, remember in the reaction coordinate diagrams, you'd have enough energy to get over the bumps if you're at a high temperature. Well, here, the K will change when you change temperature. That's the only time K is going to change. If you change the temperature, K will always change. And that's how temperature is directly related to rate, because it changes this factor of that. Okay, that's the rate law of a rate determining step. That's an elementary step that happens to be the first step. Taking a look at the second one, here's my overall reaction. I want to find the mechanism for it, so I go find the slow step, and I'm going to write the rate law for that. Rate equals K times N2O2 and O2. N2O2 and O2, the concentrations of each. And then I double check. Okay, taking a look, is N2O2 or O2, is either of them a transition state? I can see that N2O2 is made and consumed. So yes, that's a transition state, which means I can't have it in my rate law. Luckily, it always has this fast reversible one that we can kind of deal with. So I'm going to take a look at this fast reversible one. Let me change colors here. So I'm going to write the rate law for this top reaction. I'm going to say that rate equals K times NO squared. That's for going this way to the right towards the product. But it's a reversible, so the rate is also going backwards. So rate equals K times N2O2. That's for going backwards. And we know that these two rates right here are actually going to be equal to each other because it's equilibrium reversible reaction and fast. So if I know that those two are equal to each other, then actually what I know is N2O2 is actually going to be equal to this NO squared. So I'm going to take this part right here and blop it in there. So my overall reaction is rate equals K times NO squared, because I can see that these two are equal to each other. Boop, times O2. So this bottom one is my actual rate law for this reaction. I cannot have a transition state in my rate law, so that's why I had to kind of manipulate it around to make it work. Last thing is looking at graphical analysis. I'm good on time. So taking a look at the graphical analysis, you're going to use open notes, so this is fabulous. I would straight up put in my notes like the 0, the first, and the second order here. So here's my 0 order reaction. You will have a straight line if you've got the concentration versus time. Concentration is really our key part here. This could be a little bit different down the bottom. Here it's ln of whatever you've got versus time. And here it's 1 over that concentration versus time. So this would be a second order reaction when it's 1 over something. First order reaction is the ln of it, and the 0 order reaction is, I don't know, plain. It's nothing of it. So in this example, I find the thing that has a straight line. 1, 2, I would have to say this graph has the straightest line. It's the most linear, thus this would be a second order reaction. And if they asked you, like looking at the graphs, what is the order of the reaction? You can just say, it's a second order reaction because it has the most linear. Boom. Done. You just have to state that it has the most linear graph. Okay, the other part of this I want to talk about is what if you're only given one graph, right? Taking a look in this bottom part here, this is only one graph. It says you have only one graph. What is the rate law? Well, 9 times out of 10, it's going to be a half-life situation, and that's what this is. If you're only given one graph and you're asked to find the rate law, think half-life. It's all about half-life then. So if I look at the concentration of 1, and then suddenly it's at 0.5, half of its starting, and that took 20 seconds. If I do another half, 0.5 to 0.25, you can see they got a dot there, and that's 40 seconds. This is the same amount of time. Every time they cut the concentration in half, you've had 20 seconds go by. 20 minutes, sorry. 20 minutes goes by, and half of it drops down. It has this particular shape, too, that's pretty indicative. So this, I know, is going to be a half-life problem. I can determine the half-life, 20 minutes, and any time that you have a consistent half-life, it's going to be a first-order reaction. And that's the only type of half-life stuff you're going to do in AP. So I can see it's a consistent half-life, first order. So if I had to answer it, what's the rate of the what order reaction is it? It's a first order because it has a consistently the same half-life of 20 minutes each time. Done. So let's take a look at this graph over here on the left. You can see that I've got the different options here. I've got regular, looking at pressure instead of concentration. I've got the ln of it, that's the first order sort of thing. And I've got the 1 over. So if I'm asked to determine, like, what's the rate law of this, not the rate law, well, I could determine the rate law, that'd be fine. What's the order of the reaction for this one? I'm taking a look at it, I'm saying, okay, I could graph it. I could graph each of these, and I could tell me which one's most linear. But then I'm also looking at, whenever you're asked to do that, you don't really have the graphs there, 150 divided by 2 is 75. 75 divided by 2 is about 38. 38 divided by 2 is about 19. This right here is another half-life situation. It's cut in half every single time we do 100 minutes. So this, again, is a first-order reaction. I'm betting if you graph it also, you're going to see that the ln is going to be the most linear. So that works out. I hope that helps. That's my update.